Okay, so in this video, we're going to be talking about how to synthesize alcohols using both aldehydes and ketones. Mostly, this video will be going over different reduction methods that are useful for this. So let's start. First, we're going to talk about reduction using NABH4. The process for using NABH4 is extremely similar to using LiAlH4 below, but we'll see that in a second. So starting off, we have our aldehyde here, and we want to form an alcohol. So what we can do is we can do a nucleophilic attack using the hydride ions connected to our boron. So these hydrides, will attack, because they're delta negative, will attack the backside of the carbonyl group, because that side is delta positive, and these electrons will move up to the oxygen. So that's our nucleophilic attack, and this forms an unstable oxygen with a negative charge. Because we want to form an alcohol, we need to do a proton transfer, and we can use water or a strong alcohol for this. In this case, we're using sodium hydroxide. I'm going to use the hydrogen from sodium hydroxide. So these electrons on the oxygen will grab the hydrogen, and then the bond between the hydrogen and the sulfur will, those electrons will go back. So that gives us our alcohol group. Yeah, so that's using NABH4. Next, let's talk about reduction using LiAlH4. So in this case, we can use a ketone. Using a ketone or an aldehyde in these types of reactions, the method's the same. Just depends on what you want to form. In this case, we formed a primary alcohol right here because we used an aldehyde, but we might get a different result with our ketone. So we're starting with our ketone, and we have our lithium and our aluminum connected to the hydride ions, just like the boron was above here. So these hydrogens, delta negative, and the lithium-aluminum H4 molecule is really good in solution because it likes to dissociate. So, yeah. So then these hydrogens will attack the backside of our carbonyl group because it's carbon delta positive and the oxygen is delta negative. So these electrons will move up to the oxygen. That's our nucleophilic attack step. And now we have an unstable oxygen with a negative charge. And just as before, because we want to form a alcohol group, we can use water or a strong acid or just an acid. In this case, we're using a hydronium ion, and that's fine. So we'll use these electrons from the oxygen to grab our hydrogen. These electrons will go back to the oxygen, and we will form our alcohol. And like I was kind of leading up to before, this is a secondary alcohol because the alcohol is attached to a carbon that is attached to two other carbons. And we also form water. Okay. Next, let's talk about the Raney nickel catalytic reduction mechanism. So typically what I've seen is that the Raney nickel catalytic reduction mechanism can be used to reduce really any double bond. But in this case, we're using it to reduce our carbonyl group double bond. So to show this, essentially, we're using a hydrogen or an H2 group that looks like this as a molecule. And the thing about a hydrogen-hydrogen bond is that at any point in time, one of these hydrogens will be delta positive or delta negative, and this is essentially called the dipole moment. So let's just say that at this time the reaction's happening, this hydrogen here is more delta negative than the other hydrogen it's attached to. And so this delta negative hydrogen wants to attack something positive. So it will attack the backside of our carbonyl group, and these electrons will go to the oxygen, and then this hydrogen-hydrogen bond will break, and the electrons will go to the other hydrogen. Well, actually, no, that's not true. Hydrogens will break. Okay. And then this is our product, so I'm going to move this over here, and we're not there yet. But we will end up with an unstable oxygen connected to our group and 2 hydrogens, and also our remaining hydrogen, H+, from the molecule that we just broke. So it's useful because all we really need is the 2 hydrogens in solution. And because we want to form an alcohol, these electrons will grab the hydrogen, H+ in solution, and form our alcohol. So that's that one. Next, let's talk about reduction using a strong nucleophile. In this example, I used cyanide, or more specifically sodium cyanide, because this molecule likes to dissociate in polar solvents, and so it's really easy to use. And so eventually we'll end up with a negative carbon connected to its nitrogen. And so these lone pairs are delta negative, and they want to attack something delta positive. So they will attack the backside of the carbonyl group, and these electrons will go up to the oxygen. Okay, and then this is our nucleophilic attack. We now have our cyanide group attached, and we have an unstable oxygen. Because we want to form an alcohol, we need to use these electrons, and they need to attack the hydrogen on a hydronium ion. We can use strong acid, an acid like this, or water, for example. It doesn't really matter too much, but using an acid is useful because we know the hydrogens will readily dissociate. So the oxygen electrons grab the hydrogen electrons between the hydrogen and the oxygen move back to the oxygen, and we form ourselves an alcohol group. Okay. Next, let's talk about reduction using Grignard reagents. So first, I think we need to talk about how we formed our Grignard reagent. The Grignard reagent is this right here. A really good way to kind of show this is by doing this. And magnesium and ether. So magnesium wants to attack an alkyl halide. It's really easy to attack the bromide because the bromide is a -1 charge. Magnesium's typically a +1 charge. But essentially the magnesium sandwiches itself in between the carbon and the bromine. It forms this. And then the magnesium bromide just becomes a super easy, a super good leaving group. So we have that. And now we have our Grignard reagent. We know that our magnesium is going to be delta positive, and the carbon that it's attached to is going to be delta negative. So we know that our delta negative carbon wants to attack the backside of our carbonyl group because that carbon is delta positive. And so when that attacks, these electrons will move up to the oxygen. And we will get this, an unstable oxygen with a negative charge. And then this is our, the remains of our Grignard reagent. Notice that we only have 1, 2, 3 carbons, and that's because our magnesium was attached to 1, 2, 3 carbons. So it's just important to count and make sure you're not adding too many or too little when you do the Grignard reagent. Okay, and then next, because we want to form an alcohol, we can use a hydronium ion, and we can, these electrons on the oxygen will attack that hydrogen, those electrons move back to the oxygen, and we have ourselves an alcohol. Yeah. Right. Next, we have the process of hydration. In other words, it's just the process of forming a hydrate. A hydrate looks something like this, and it's just having a hydroxy group connected to a carbon, essentially. So it's really useful to use water, hydronium ions, in this type of reaction, because you don't want to add on any extra R groups or anything you don't need, because all you want is to add an OH group or two. So first we need to activate our carbonyl group. So what we can do is we can use a hydronium ion, or we can use a water and then activate the water to make it positively charged. But we want these electrons on the oxygen to easily be able to grab a hydrogen, and it's useful that the hydronium ion is acidic and so wants to dissociate its hydrogen. But essentially, these electrons grab a hydrogen and we get an unstable oxygen here. And this is, I'm just going to write active. Okay. So next, this formation is very useful, because not only have we set ourselves up to create a hydroxy group, but we have this double bond, and we know that we can do a carbonyl nucleophilic attack and attach on our water group, and then turn this oxygen group into a OH group, or an alcohol. So I jumped ahead of myself, but essentially this is a nucleophilic attack. These electrons want to attack the backside of the carbonyl group, and then these electrons will move up, and we'll get our alcohol group, which is what we want. And now we have a water group essentially attached to our essential carbon. And this is fine, but because we want to make a hydrate or two hydrates, we need to make another alcohol, and to do this we need to take a hydrogen off. So we can just use water, and these electrons can grab that hydrogen, the electrons move back down, and we get ourselves a hydrate and a hydronium ion in solution. But this is our main product. Okay, next and finally, we have our hemiacetal formation. So just to review what that is, hemiacetal in relation to the hydrate looks like this. It's half hydrate basically, and then half acetal. And acetal looks like this. It's basically two ether groups, because these R groups are essentially just carbon groups. So that's why in this next reaction, we're not only going to be using water, we're going to be using some sort of ether reaction with a carbonyl group. So we have our carbonyl group right here. And I believe we can use water for this step as well, but all we want to do is activate this group here so that it wants to react with our carbonyl, or vice versa. So what's happening is that these electrons are going to grab the hydrogen from our acid, because our acid is readily going to dissociate hydrogen into solution. So that means we will form a very unstable molecule here with an unstable oxygen. And that's good, because now this is now active and ready to react, and also ready to dissociate any of its hydrogens, really. So that means that our carbonyl group can grab a hydrogen from solution and become active itself. So now this molecule is unstable because our oxygen is positive. And finally, because we want to form an ether group, we want to react this active molecule with some sort of ether molecule. In the last mechanism we did, this step is basically exactly the same. We had an active carbonyl group in both scenarios, an active carbonyl group that now wants to react with a nucleophile or is open to being reacted with by a nucleophile. In this case, we used water because we knew we wanted to form another alcohol group, and we had an alcohol group already kind of set up to be made. In this next problem here, to make a hemiacetal, we know we have an alcohol group set up to be made because we have an OH bond here, but now we want to add an ether group to make a hemiacetal. So we're going to use an ether nucleophile, and these electrons on the oxygen will attack the backside of our carbonyl group, moving those electrons back up to the oxygen, forming our alcohol group, and now we have this extra group on the side, and that's unstable. And now because we know we want to make an ether and not an alcohol, we are going to use, you could use a base, you could probably use water if you really wanted to, but the idea is that you have electrons that want to take the hydrogen off of the oxygen, and so these electrons move back down, so you get your hemiacetal. Yeah. So that is all I have, but essentially the main idea, I think, besides, mostly hydration and hemiacetal formation, is that these mechanisms are pretty standard. We use them for, reacting with alkenes or even alkynes to hydrate these groups. But in this case, we're just using our carbonyl group, which is just another double bond, but on one side is an oxygen, and on the other side is a carbon. So just knowing these reagents and these mechanisms is really useful for even other problems that we learned in the past. But that's essentially reduction of aldehydes and ketones to make alcohols.